The last class we were talking about probability distribution and we started talking about standard distributions which we call as theoretical distributions, and we learned Bernoulli distribution and we saw how binomial is defined from the Bernoulli. So that's enough. If you remember the distribution PMF, how is it defined, and then few examples and what are its mean and variance, and maybe one or two simple problems which we do in the practical class, which helps in understanding and computing the probabilities of binomial distribution. So this is the definition. Any discrete random variable x is said to follow binomial distribution if its probability distribution function or the probability mass function is given by the mathematical form p of x is equal to ncx p power x q power n minus x, where x takes the value 0, 1, 2, etc. up to n. P is called as probability of success, which lies between 0 and 1, and we define q as probability of failure, and q is equal to 1 minus p. Then if this happens with the set of x values, then we say x is following binomial distribution. Now, if you remember, binomial distribution is nothing but sum of n independent Bernoulli trials. So we are taking repeated Bernoulli trials and we are counting how many success we had in total. So we are counting how many success we had in total. Then the number of success also follow binomial distribution. On the other hand, if you count your excess number of failures, they also follow the same distribution, but not together. If you're counting excess success, then success follows a binomial distribution with probability of success p. If you take excess the number of failures, then x follows binomial distribution with probability of success q. So it changes that. So we looked into the definition and we also learned what are the mean and variance of the binomial distribution. Now for you in the examination question will be define binomial distribution, give some examples of binomial random variable. So what are we talking here? We are talking about a Bernoulli. What is Bernoulli? Bernoulli is a case where a single experiment trial has two outcomes, which we generally call as success and failure. So come up with those examples which are basically Bernoulli, and then you are talking about a lot of Bernoulli. Now we learned that tossing a coin is a Bernoulli, throw of a die is a Bernoulli, and then giving birth to a child is a Bernoulli experiment. So in coin there are two possible outcomes, heads and tails. You can call either success as heads or success as tails. Then in the throw of a die, you define what is success. Die actually has six outcomes. Now these six outcomes had to be grouped into two outcomes so that you can easily define success and failure. So if I say getting an odd number is success, getting an even number is failure, then whenever you throw a die, you will either expect a success or a failure. So in that situation, throw of a die also becomes a Bernoulli trial. Now we say binomial is the repeated Bernoulli. So instead of saying toss a coin, now you can say toss six coins, toss eight coins, or toss up one coin 10 times, toss a coin four times, etc. And then count what is the total number of heads or total number of tails you observed. Then the total number of heads, total number of tails in that total trials of those coins becomes a binomial variable. Now, when I say we are tossing four coins or four tosses of a single coin, they're almost one and the same. And if I say x is equal to number of heads, then I'm tossing four tosses together now. So if you toss the coin four times, how many heads are possible to observe? Now all the four tosses may result in tails. So in that case, x is equal to 0. That is one possibility. Out of the four, only one toss may lead to head. The remaining three could be tails. That is another possibility. Two heads is one possibility, three heads is one possibility, and all the tosses may show heads. So four heads is another possibility. So if I toss four coin, the number of heads takes value 0 to 4. So if I toss 6 coins, the number of tails, if you are modeling the distribution for number of tails, number of tails also takes the same values 0, 1, 2, 3, 4, 5, 6, because we are tossing 6 coins there. So these are all examples of binomial variate. And again, counting the number of male children in a family of 2 children. So you're visiting or you're doing some surveys on the families. You have selected only those families which have maximum of 2 children. Now, of the maximum of 2 children, now we are counting how many male children are there. So since the maximum is 2, the number of male could be 0, which indicates both are female. Number of males could be 1, indicating 1 male and 1 female child in the family. Or number of males could be 2, indicating all the children are male in the family. Now, similarly, number of bombs hitting the target among the 3 bombs which are aimed at it. So you are uh, dropping 3 bombs on the bridge of the target, and you are, you know, you want to see how many will, successfully hit the target. Then the number of bombs hitting the target becomes your x. That again takes value 0, 1, 2, 3. So I have understood that you can generate binomial only if you specify this n, where n is the number of times a Bernoulli is repeated. Now dropping a bomb, the bomb has, two outcomes. Either it will hit the target or it will not hit the target. Therefore, it is the Bernoulli. Number of defective articles in a manufacturing lot. So whenever an item is produced, it takes two categories. Either it is defective or non-defective. So it is a Bernoulli experiment. Now we are taking 6 such articles from the production, and we are saying how many articles are defective. In this 6 randomly selected sample. Then again x takes the value 0 to 6. So if you fix some n and count how many is going to be success, then always that number of success follows binomial. Even if you count the number of failures, that also follows binomial. We have studied a lot of properties when we discussed the analysis of distribution, like mean, median, mode, you know, skewness, kurtosis, etc. These are some of the important properties. Now, as said, our binomial distribution is based on what is the value of n and what is the value of p. So if you know the value of p, you can easily obtain the distributional properties like mean, variance, standard deviation. You can also see what exactly the PMF is. Once you know the value of n, you can say what are the possible values of x, and then you can just remember these two. For a binomial and Bernoulli distribution, mean is always greater than variance. So 5 to 6 properties are sufficient for you to memorize. And this is one important property will be asked. So property number 11. And talking about the skewness, there are 3 cases. The distribution could be symmetric. So this happens when our value of p is equal to half. We know that p takes any value between 0 and 1. So if we have p exactly equal to half, in that case, the distribution becomes symmetric. So we'll look into this when we talk about the problems in the practical class. On the other hand, if you have the value of p which is less than half, then the distribution is positively skewed. If the value of p is greater than half, then the distribution is negatively skewed. Now, p less than half automatically indicates q greater than half, because we have defined q probability of failure as 1 minus p. So if your p is less than half, automatically 1 minus p will be more than half. So we say q greater than half. So you need not memorize both. So just learn the statement with respect to p. P equal to half, symmetric. P less than half, positively skewed. P greater than half, negatively skewed. And this skewness is captured by the measure called as beta 1. Beta 1, gamma 1 are the Karl-Pearson coefficients. I haven't given you the formula for beta 1 yet. So This is also in terms of N and P for a binomial distribution. So beta 1 is used to look into the skewness of the distribution. There are three types of skewness: no or zero skewness, indicating symmetric; positive or right skewness; negative or left skewness. Another important property is the foundation for the next distribution, which is also a most widely used distribution, called as Poisson distribution. Ozone is a French mathematician who observed this particular distribution. So this happens when in our binomial n is very large, but p is very small, but the product n into p is taken as a constant. That is, this is working, under the limit. So we have a case where n is increasing, that is the number of trials of Bernoulli is getting larger and larger, probability of success is becoming smaller and smaller. And then np, if you look into the product n into p, it is somewhat, taking a constant value. So this is another Greek letter, lambda, which is used to indicate the parameter of the Poisson distribution. So if these two conditions are satisfied, that is n is large, p is small. So tends to infinity doesn't mean that n is taking really infinity, tends to indicate that it is becoming larger and larger. So as n becomes larger and larger and p becomes smaller and smaller, what happens with the PMF is that we have to look into NCX. Now, if you have your calculators, scientific calculators, you can see what is the difficulty in computing NCX when you have larger value of n. That is the combination, right? So if you just say 4C2 or 4C3 or 6C2, that itself is coming to be 15, 6, 8, 3, 4 observations, 4 values. When you say 100C2, when you say 50C2, when you say 100C3 or 20C3 for that matter, it becomes a larger value. So the number of possibilities as n increases, the value of NCX also increases. Now, along with NCX in the PMF, we have the next term, which is p to the power of x. Now, x is the number of success, but we have p probability of success to be very low. It is somewhat like 0.01 or 0.009, 0.1. And if you say 0.001 to the power of 10 or 0.01 to the power of 20, then it literally becomes equal to 0. So your PMF is always taking the value 0 when your P becomes closer and closer to 0. So this PMF, binomial PMF, fails in giving the probabilities. So we have to work under the limit and see what exactly is happening. And when we do that, we get a new distribution called as Poisson distribution. And whenever in a binomial n is larger and p is smaller, the Poisson distribution could be used. Now, similarly, another distribution, common or most widely used distribution, is normal distribution. And normal distribution comes into picture when we have a binomial where again n is large but p is not small, but they are close to half. So P and Q almost equal and Anrartha. P is taking a value closer and closer to half. So if P becomes closer and closer to half, naturally Q also becomes closer and closer to half because Q is equal to 1 minus P. So we say P and Q are almost equal. So remember these two properties, they could be specifically asked: under what conditions binomial tends to Poisson, under what conditions binomial tends to normal. And then other question commonly asked, only one possibility in the theory: define binomial distribution or write a note on binomial distribution. So when the question is define or write a note on binomial distribution, you define the PMF, take one or two examples and write 5 properties at least. So this is the definition. So write this, memorize this. So it is in that second PUC textbook. You can mark the page number 150 onwards. And then these things are not required, that we'll see when we take some problems in the practical class. And then see some examples. Remember, at least 3 examples and some properties. So that is sufficient to talk about binomial in the examination. Okay. So other things are not in your syllabus, you need not worry. Just those things are sufficient. Okay. So can have a look into the numerical problems, how the binomial is applied, but we'll see that in the practical class, so you don't worry now. Next distribution is Poisson distribution. Said Poisson is another discrete distribution that also happens for x is equal to 0, 1 and so on. But as said, it is the limiting form of binomial. That is, in a binomial, if n is large and p is small, in that case that gives generation to a distribution called as Poisson distribution. So this is the definition of Poisson. Now it is purely, mathematical form. Some of you might feel it is very much difficult to write and understand. It's not that difficult actually. So it is using a mathematical constant, which is E. The value of E is 2.71, and we know lambda. So lambda is the real number which is taking any positive value, and that is said to be the parameter of the distribution. So once you observe lambda, you can compute the probabilities for any particular value of x using the formula e power minus lambda, lambda power x by x factorial. Now in your case, e power minus lambda, you can generate it from the scientific calculator. So if you don't have scientific calculators, then you have to use the tables in order to obtain e power minus lambda, or in practical cases in the questions, e power minus lambda may be given in the question itself for a particular lambda. Okay, so we'll look into those cases in the practical classes. So today we'll just understand the definition, and we will see what are the examples, what are the properties of this distribution. So as said, this is also a discrete distribution. So it is again, the application could be wherever you are counting the number. So especially here also, as said, x is the number of success in the Bernoulli. If the number of success is becoming larger and larger, but the probability of that is becoming smaller and smaller, in that case we talk about Poisson distribution. You can see Poisson distribution is used when probability of success of an event is very small. But we don't talk about the problems from converting the binomial into Poisson. We'll only study purely the Poisson problem. So if you look into the values of x here, it is taking 0, 1 to etc. up to infinity. So infinity is just a notation which indicates that something large is happening. So that doesn't mean that your x is always infinite. It takes infinite, because in the practical cases, reaching infinity is not that possible. For example, say, think a case where n is large. So there is a large production of items happening. So you are producing hundreds, thousands, lakhs of items. And in most of the cases, so when you look into the case, the item may be clearly classified into a failure or a defective. So in that case, your probability of success is becoming small and small. So every item which you're producing has one or two defectives in them. So that is the case, but that doesn't mean that all the items produced are defective, or also it doesn't mean that all the items produced are non-defective. So in that case, we can talk about Poisson distribution, and you cannot exactly say what is the maximum number of defective observed, what is the minimum number of defective observed. Therefore, we say it is 0, 1, 2, etc. up to infinity. So until and unless you conduct the experiment and see, you can't observe what is the maximum value of the x there. So in those cases, you can easily say the variable follows Poisson distribution. Okay, so any discrete random variable follows Poisson distribution if its PMF is given by P of x is equal to e power minus lambda, lambda power x by x factorial. Whenever you write the PMF for a variable, its range or support, that is the possible values of x, that has to be written across that, and also the constants used in the distribution, their range, their values also has to be written. So in case of binomial, we say x equals 0, 1 to n, and 0 less than p less than 1, p is the parameter there. Here lambda is the parameter. Lambda can take any value greater than 0. You can have lambda Poisson distribution with lambda 0.1. You can have Poisson distribution with lambda 10. You can have Poisson distribution with lambda 3.1, but lambda doesn't take the negative values. So this is the mathematical number E, takes value 2.71. So you need not remember that. Your calculator, scientific calculator easily produces that. So you can use that in obtaining the probabilities. Now coming to the example. So here we are talking about a success case where we have n very large, or you cannot give the maximum value for that particular x. So in this case, we say variable follows Poisson distribution. So variable follows Poisson distribution if okay. First example, number of deaths occurring in a city in a day. Now you exactly cannot tell the deaths will be 10, deaths will be 20 in a day, but the possible values could go on like 0, 1, 2, etc. So you cannot give what is the maximum deaths in a day. So you can observe it. In the yesterday it was maximum observed in the city was 100, day before it was 10. So after the completion of the day, you can come up with the exact value. But prior to that, you can only have a guess, and hence we say x, the number of deaths could be any value of 0, 1, 2, etc. up to infinity. So this doesn't mean that on a day there will be infinite number of deaths. So infinity here we say, we write it indicating that the exact maximum value cannot be written. It could be a large number also. Again, number of road accidents, you cannot exactly say how many that will be. So you can just say x equals 0, 1, 2, and so on. Number of incoming telephone calls at an exchange in 1 minute, in 10 minutes, in 1 hour, whatever may be the time span. Number of vehicles crossing a junction. Number of complaints received. Number of customers arriving at the supermarket per hour. Number of printing mistakes per page, number of bacteria in 1 cubic centimeter, number of radioactive particles emitted from a radioactive substance in a fraction of a second. So all these cases are examples of Poisson distribution. So I said, you please memorize 2 to 3 examples of binomial as well as Poisson. Now you are clearly understanding the difference. So these variables, in case of binomial, we didn't talk about number of deaths, number of road accidents, number of telephone calls. So there we fixed the value of n, and then out of n we counted how many are there. So visiting family of 2 children and counting how many male children or female children. Sowing 10 seeds and counting how many got germinated. So even in this cases, if you could somehow bring that concept of n, then the variable automatically becomes binomial. But it is hard to bring that n here. So you cannot say number of deaths out of, so you can say number of deaths out of 10 people, 10 patients who are on observation. So you are observing 10 patients, and out of those 10, how many are dying? That could be counted. In that case, it becomes binomial. So that is a very rare scenario. And similarly, you cannot fix n here, or number of road accidents in a city in a week. So if you put the value of n as number of vehicles, like say 20 bikes are passing in this particular traffic junction, then out of these 20, how many bike will get, how many accidents will happen? In that case, you can say number of accidents out of 20 becomes binomial. But since we leave it for a week, a day, and for a particular time, you cannot fix the value of n. Therefore, all these come under the example of Poisson. Now, as we have some properties of binomial, we have certain properties of Poisson distribution also. So we are now quite familiar with the PMF. It is P of x is equal to e power minus lambda, lambda power x by x factorial, where x takes the value 0, 1 to infinity, and lambda is the parameter greater than 0. Binomial has two parameters, n and p. Poisson has only one parameter, lambda, where lambda is greater than 0. This is the range or the support of the distribution. And for a Poisson distribution, you observe that mean and variance are one and the same. Whereas in case of binomial, mean was NP, variance is NPQ. So there we observed mean greater than variance because NP is common here. Q is a number which is less than 1. When you multiply a number with less than 1, automatically the product becomes lesser. So we said mean is greater than variance. So variance becomes lesser when you multiply Q with NP. So mean is greater than variance in case of binomial, whereas mean is equal to variance in the Poisson distribution. So the question could be name a distribution where mean and variance are same. The answer is Poisson distribution. Name a distribution where mean is greater than variance. Answer is binomial distribution, Bernoulli distribution. So these properties are sufficient. And again, whenever you observe that lambda is greater, then the distribution always becomes normal distribution. So that's why we have to study what is this normal distribution, because most of the variables, though it is discrete, it can be studied under a distribution called as normal distribution. And just remember these two properties also. Poisson is always positively skewed. Poisson is always leptokurtic. Skewness is measured using beta 1. Kurtosis is measured using beta 2. We have only talked about Karl Pearson and Bowley's skewness. I know we haven't talked about this beta one. Maybe if time passes today, we'll talk about that. Fine. So this is about the Poisson distribution. So again, numerical problems will be such that lambda will be given to you. So using the lambda, value of lambda, you have to compute various probabilities. Okay, so that we'll see in the practical class. So next we'll move into the next distribution, which is normal distribution. There are other distributions in this textbook. You need not worry about those cases. For you, for biostatistics, only binomial, Poisson, and normal distributions are sufficient. So we have talked about, frequency distribution. In frequency distribution, we had discrete frequency distribution and continuous frequency distribution. Similarly, in case of probability distribution, we'll have, discrete distribution as well as a continuous distribution. So in the two cases, what we have just learned, x is equal to 0, 1 to n, x is equal to 0, 1 to infinity, there both the values of x are discrete. Therefore, binomial is a discrete distribution. Poisson is also a discrete distribution. The next distribution is for a continuous random variable. So if I have x, which is a continuous random variable, and now we, as said in the very introduction class to the distributions, whenever we talk about discrete distributions, we call their probability function as probability mass function, because you can obtain the mass of the probability, what exactly the probability that could be obtained. Therefore, we say probability mass function. In case of continuous variables, probability becomes the area. Concept of area comes into picture when you look into the density. Therefore, we call such distributions, continuous distributions, as probability density function. And even you can observe the difference in the notation. There in the left hand side, you wrote P of x, where P indicated the probability. Now the right hand side doesn't indicate the probability, it indicates the shape or the density of the curve. That's why it is giving you a mathematical function. Therefore, we use f of x instead of using p of x. There is nothing wrong if you use p of x here and f of x there in binomial and Poisson. Notations doesn't, give you the definition. The definition is important. Whether you use f of x or p of x, it doesn't matter. But you should know what do you mean by f of x in a continuous case, what do you mean by f of x in a discrete case. So if you say f of x equals e power minus lambda, lambda power x by x factorial, then you mean that f of x is probability function. On the other hand, if you are using f of x is equal to this, which is 1 by sigma. Now this is the sigma symbol we are familiar with. We use this in indicating the standard deviation. Then another symbol which we need is this, which is again a Greek letter, which is mu. So sigma and mu. So these are the most widely used notation in the field of statistics and data analysis, where this mu indicates the mean and sigma indicates the standard deviation. So you can have, many of the companies which deals with data analysis, they have their name based on these two symbols only. You have a company called as mu sigma. Company name itself is mu sigma there. And then you have a company with 3 sigma, company name with Six Sigma belt. So you can just see that how vast this normal distribution is. Just based on its notations, people are giving the names for the companies. So normal distribution is a wide application. Let us first understand the terminologies here in the PDF. PDF stands for probability density function. So you have sigma standard deviation, then square root of 2 pi. So you have that in the denominator. Then again you have this mathematical constant e, which is equal to 2.7183. So e power minus half into x minus mu by sigma whole square. So this entire thing is in the power of e power minus half x minus mu by sigma whole square. Now coming to the range of x, now in the previous two cases, we saw that x is 0, 1 to n, x is 0, 1 to infinity, almost positive cases. Now we are talking about a case where x could be any value, any real value. It could be negative, it could be positive, but we say sigma is always greater than 0. Sigma is one of the parameter and mu is another parameter. So they have missed the range of mu here. You can write it. Mu also lies within minus infinity and infinity. Because mu is mean, if I have some negative values of x, there is a chance that my mean is also negative. Therefore, your mu takes the values between minus infinity and plus infinity, but sigma takes the value greater than 0. So you have to memorize this. So this line is important. So if they ask, write a note on normal distribution or what is normal distribution, then start with this. If x is a continuous random variable, with the probability density function f of x is equal to 1 by sigma square root of 2 pi into e power minus half x minus mu by sigma whole square, sigma greater than 0, minus infinity less than x less than infinity, minus infinity less than mu less than infinity, then x is said to be the normal variable or x is said to follow normal distribution. This is the definition. And also in the early classes, I told if you want the probability for exactly equal to x in case of continuous distributions, we cannot give an answer and we say that is always equal to 0, because the reason is our x is taking infinitely many values. Then if you say what is the chance that it is taking a particular value, so that particular value is 1 out of infinite possibilities. So if you apply the mathematical definition m by n, your m is just 1, n is infinity, because you're talking about infinite set of observations. So we say probability is zero. So that is one interpretation. Another interpretation is that your x is continuous. When we say that x is continuous, you cannot exactly specify the value of x. You cannot exactly specify the value of x. So even your age, your marks, your weight, height, they're all continuous variables. We have come up with certain machines or scaling techniques or the tools which tells us what is our age, what is our weight, but it just gives us a precise value. So if you weigh your weight and observe that your weight is somewhat 56.5, then the machine is set such that it gives you the value only up to one decimal digit or two decimal digit at the max. But in reality, your weight is exactly, taking many such decimal digits after the decimal point. It is very rare that your weight is exactly an integer or exactly takes only one decimal number. So the machine is just giving you the very good approximation number for your exact weight, but your exact weight cannot be quantified. That's why we say you cannot actually observe what is the exact value of x in case of continuous distributions. Therefore, we say for continuous distributions, you cannot compute probability for x is equal to x. And even if you want what is the answer for that, that will be always equal to 0. But whereas for discrete case, you can actually count. You can actually see how many accidents are there, how many children are there, how many non-defectives are there. So exact count could be obtained. So you can have answer like what is P of x equals 3, what is P of x equals 4. You can actually compute the non-zero probabilities there. Whereas for a continuous case, you can always come up with the probabilities less than something, greater than something, or in between something. So this is the difference between discrete and continuous distribution. So we have less than 1 minute. I have to join my PV.